Okay, ionic radius, this is the distance from the nucleus to the outer energy level of an ion. An ion, if you can recall, was a charged atom. I do have a video on that. You can take a look. And metal ions become smaller. We briefly talked about this. Cations are positive. Why are they positive? Because they lost electrons. So when I said that cats are small, so it's an easy way for you to remember that metal ions that are cations are going to become smaller than their original atoms. Why? You lost an electron, it loses an energy level. That's really it. I think that's kind of common sense. You lost the electron, it's going to get smaller. Okay. All right, so taking a look at the comparison before, that was atomic radii. We saw the trends that we saw before. And now we're looking at ionic radii. So as you can see, the little ones, these are your cations. Cations are positive. They are also tiny. Cats are small. And then these big chubby ones over here, these are your anions, the negative ones. And they are larger, and that makes sense because they've added electrons. They're all going to be getting bigger because they added some electrons. Okay, and just by simply adding them, we've made them larger. All right. Sizes of ions. Electron repulsion. Valence electrons do repel each other, so you don't want to sit the electrons next to each other because opposites do attract and the sames are going to repel. So valence electrons are all negative. They're going to repel each other. So when an atom becomes an ion, adds an electron to the valence shell, the repulsion between these also increases. So in addition to the fact that we're adding an electron and we're adding more stuff, electron's not really that big. It's really moving very fast. Again, small mass. It's not a huge difference, but it's an easy way for you to remember that. But what's really happening is that the electrons just want to be so far away from each other, it's not even funny. So when you add another one to the mix, whew, they're really going to spread out. Okay, so here we can kind of see that they've spread out a bit. We've added now another one. So F ion, so the fluoride ion, so F1 minus, is larger than fluorine. Okay, so you added one, it's now a little larger. Okay, and the distance between these two, as we add the one, take a look. All right, everything's kind of has to shift accordingly to kind of be further away from each other. And that in turn builds up and makes that shell larger. Okay, and spreads it out. Yep, and there you go. All right, so electronegativity, we briefly mentioned this before. All right, the ability of an atom and a molecule to attract the shared electrons to itself. So basically, it's the desire to want that electron. It's the want of that negativity. Electronegativity. I want to be negative. I want my friends the electrons. So this scientist, Mr. Pauling, died 1994. He gave us this idea here, so he gets the credit. So there we go. So here's your trend in the periodic table. So what's happening? Electronegativity increases from left to right across the period. That kind of makes sense to us. So if it wants an electron, who wants an electron? Non-metals, because metals, remember, are losers. So if this electronegativity just basically means something that really wants an electron, obviously these non-metals really want electrons, so versus the metals who don't. So as we go from left to right towards those non-metals, this value should increase. They want the electrons. Okay, as we go down, though, electronegativity decreases from top to bottom. So just taking a look, we have our metals over here, and you can see they really don't want an electron. Their numbers are really low. How high does this really go? Let's take a look at who the highest one is. All right. Okay, so we're getting more. We're going from a 0.8 to now a 2.4. And as we get closer, who has the highest electronegativity? Fluorine. So fluorine really, really, really wants an electron is what this means. He wants an electron more than anybody else. Who does not want an electron? who has the lowest electronegativity. So if it's not him, let's try to see maybe in the opposite corner. Ah, yes. So here we have cesium and francium tied into the, I guess, first place of having the lowest number. They desperately do not want an electron. They do not. They want to lose their electron. And if you can recall, group 1, they all want to lose 1 electron. Group 2 want to lose 2. All right, ionization energies, I know we briefly talked about. Energy used to remove an electron from the atom to form a cation. So it's how much energy is needed to get rid of an electron. Is it an easy thing? Is it not an easy thing? Okay. So larger values of ionization energy mean that the electrons they're more tightly bound to the atom. It's harder to remove. You're going to find this value as first ionization energy located on table S. So if they ask you to put elements in order of increasing ionization energy, for example, you're going to look at table S, or you could remember the trend. Here's the trend. The periodic trend says it increases, ionization energy increases from left to right. Why? As the nuclear charge increases, the electrons are more strongly attracted and thus more energy is needed to remove them from the atom. So as we're adding more electrons and protons to the mix as we go across, it's going to be harder to pull those electrons away because the attraction between the negative electrons and the positive protons is so great. All right, also, what we just talked about, nonmetals really want to gain an electron. They don't want to lose any of the ones they have. They're so close to getting 8, it's much easier for them to just gain 1 more. All right, group trend, it's going to decrease from top to bottom. Why? Because valence electrons in each element are at a higher energy level, great, and thus further from the nucleus. And it's easier to remove them when they are further from the positive charge. So because of that shielding effect that we talked about before too, as we go down from top to bottom, the atom is just getting too large. It's hard to keep track of all of the electrons, and especially because now they're in a higher shell, it's a lot easier to just take one of the electrons away. So the one with the greatest electronegativity, if you can remember, is up here at the top. Not electronegativity. Electronegativity is up here at the top. So he desperately wants an electron. So of course it's going to require much more energy to remove an electron. And if you take a look, that is consistent with these ionization energies here. Fluorine should have nearly the highest. Actually, these guys are coming in first place. Why is that? Because these guys are your noble gases. So they're perfect. They don't want to lose anything. They don't want to gain anything. So they are actually the real winners here. But if you take them out of the equation, fluorine would be the winner, which makes sense because he had the highest electronegativity. All right, so this is a really brief summary just to kind of get us up to speed here. You feel free if you need to pause the screen, make sure you know kind of basically what's going on. So this is just again a summary. If you need any of this though, and if you forget any of it, remember that they are there on table S to help you out. However, you do need to know like what the words mean, like electronegativity, ionization energy, atomic radius. You do need to know what those words mean. So make sure you understand it. But these are the trends as we go across. This is what happens in the different cases. As we go down, this is what happens in certain cases. And of course, if they ask you it the other way around though, just keep that in mind. If they say as you go up a group, what happens, just be prepared to flip whatever this is. Chances are they will go from left to right as we go across period, and they will discuss going down the group. And that's it.